Okay, so we're now going to move on to just a couple more definitions, kind of a couple things that are important to know about oxidation and reduction reactions, but nothing super big being added on here, just another couple kind of definitions, okay? So we're going to start out just by looking at this. We're going to kind of build our thing. So in the following reaction, what is reduced, what is oxidized, and what is neither reduced nor oxidized? Okay, so we begin as we always would, just kind of going through one by one, saying, hey, what's its charge before? What's its charge after? And does that mean it gained, gained electrons, lost electrons, or neither, right? That's based on the change in its charge. Okay, potassium is part of an ionic compound here, right? It's part of a compound, so that means it has its ionic charge. And potassium, if you look on the periodic table, has a charge of +1. Same goes for bromine. It's part of an ionic compound, so it's going to have its charge. Bromine, whenever it's on a compound, has a charge of -1. Now, poor lonely sodium here. Sodium's all by itself. It's just an atom, right? And all atoms have the same charge, big ol' 0, right? If they did have a charge, we wouldn't call it an atom. It would be an ion, right? But over here, things have changed for sodium, right? Now it's part of an ionic compound, right? And ionic compounds are formed by two things with charges. So sodium's charge is +1, and nothing's really changed for bromine here except for its partner, right? But it's still part of an ionic compound, and so it still has its charge of -1. And poor potassium, it got left by bromine for sodium, right? But potassium is now all alone with no charge. It's an atom, right? No charge given, so that has a charge of 0. Okay, so let's just say, hey, what happened to you? What happened to you? And what happened to you, right? We'll draw our kind of connecting pretty little rainbow here. Say, okay, potassium went from +1 to 0. Bromine went from -1 to -1, okay? Nothing super interesting there. And sodium went from 0 to +1. All right, so what does that mean? I'll give you a sec to think about it, okay? Who was reduced, who was oxidized, and who was neither, who didn't do either thing? Okay, so remember, uh, if it, on a number line, right, if this is 0, if it goes towards the negative numbers, it's getting more negative. It's to get more negative, you have to gain negative electrons, right? But if it's going to the right, it's getting more positive, which means it's getting less negative. To get less negative, you have to lose electrons. And never forget, Leo Ger, right? So if you lose electrons, oxidizing. If you gain electrons, reduction. Okay, so potassium here went from +1 to 0, right? Okay, so it went towards the negatives. It got more negative. It gained electrons. Grr, reduction. So what got reduced? Okay, maybe I'll write it to the side just because I'm going to run out of room there. Okay, okay, what got oxidized? Well, what got less negative? Well, bromine went from -1 to -1. Okay, so that's not more negative, but it's not less negative either. Sodium went from 0 to +1, so from 0 to +1. Okay, hey, it's going that way. It's going towards the positives. It's going away from the negatives. It's getting less negative. It must be losing those negative electrons. Losing electrons. Leo, Leo, Leo. So what's being oxidized? Sodium, Na. What is being neither reduced nor oxidized? Well, that's kind of the one that sticks out the most, right? Bromine went from -1 to -1. That's no change. So bromine went from -1 to -1. Okay, no change there. All right, now there's a name for those things. Okay, the first one, I'm going to go through the last one first, actually, here, just because we've been holding off on it. But bromine, okay, it was there, but it didn't oxidize and it didn't reduce, right? It was there, but it didn't oxidize or reduce. So I want you to think about this. When you are, say, at a hockey game, okay, and you are a spectator, are you there? Well, yeah, you're there, right? Of course you're there. You're at the hockey game. But are you taking part in the action, right? Are you on the ice playing? Okay. And well, not if you're there as a spectator, right? So when you're a spectator, if you're spectating, you are there, right? No one's going to say you're not there, but you are not taking part in the reaction. You're not actually doing things, okay? And I want you to notice, could bromine be kind of anything here, right? And what I mean by that is all that really mattered, the redox part, the reduction oxidation reaction, that was entirely potassium and sodium. Those were the ones that traded electrons, okay? Nothing really changes if bromine's not there. The same way if you're a spectator at a game, right? for the most part. Like if you're there and the Oilers lose, if you watch the Oilers on TV and they lose, they probably would have lost if you were there at the game in person, right? So we call that if you were spectating, right? So we call those things that are there, but they don't actually participate in the action and the reaction, I guess. Okay, we call them spectator ions. Just like when you're a spectator at a sports game, you're there, but you're not actually taking part in the action. Okay, now just a couple of definitions that are kind of annoying. I get it, a little bit confusing. We just got this oxidizing and reducing thing down, and now they're going to kind of flip it on its head a little bit, but it does make sense when you think about it. Okay, so because the K plus ion, so that's this guy here, right? It caused the sodium to be oxidized. Why did it cause the sodium to be oxidized? Remember, there's no free electrons, right? That came from the sodium. Remember, we said, okay, potassium must have gained 1 electron. Where'd that electron come from? What do you think? Notice sodium lost 1 electron. That's not a coincidence. That electron that sodium lost is the electron that potassium gained. It's the same electron. Okay, so sodium lost its electron and potassium picked it up. So in order for sodium, we can think of it the other way too, right? Sodium lost its electron because potassium took its electron, right? So in a way, the potassium taking that electron caused the sodium to be oxidized. Okay, so what we would say then is that K plus, because it caused sodium to be oxidized, it's the oxidizing agent, right? So agent, okay? Potassium did not get oxidized, but it caused something else to become oxidized. So think of that like a sports agent, right? Or an actor's agent or something. Do they actually act? Do they actually go? Does an NFL player's agent actually go on the field and throw the football? No, but they help someone else to do that, right? When you're an actor, you go to an agent and say, hey, I need you to get me in a movie. You're trying to get someone else to help you do what you're trying to do. So the sodium is the potassium is allowing the sodium to become oxidized. So it's the oxidizing agent, right? A sports agent doesn't play sports, it helps other people play sports, right? An acting agent doesn't act, they help other people act. So an oxidizing agent isn't oxidized, it helps other things get oxidized, okay? And the same goes in reverse. So because sodium caused the potassium ion to be reduced, we would call sodium the reducing agent. So quick note on that, okay? Well, let's just say the thing, don't need to be too fancy, the thing that is oxidized, what kind of agent is it? Well, it's losing electrons. So what's it helping something else do? By losing its electrons, it's helping something else gain some electrons, right? So the thing that is oxidized is always the reducing agent. So it's kind of backwards day, right? And then what do you think we could say about the thing that's reduced, right? The thing that is reduced is always the oxidizing agent. Okay, so if you're reduced, you're gaining electrons. Hey, that means you're helping someone else lose electrons, right? If I take something from you, I kind of helped you lose it, right? And then the other thing is if it's, and the other way, if it's oxidized, well, then it's losing electrons, which means you're kind of helping something else gain it, right? If you drop some money on the ground and someone picks it up, you kind of help them get that money by losing it yourself, right? Whereas if someone takes the money out of your pocket, they're kind of helping you lose the money by taking it, okay? So just kind of opposite day when we're talking about reducing and oxidizing agents. Whatever was oxidized is the reducing agent, and whatever was reduced is the oxidizing agent, okay? So really, there's nothing more to that than just figure out using your charges what's reduced, right? And then what's oxidized. And then when it's times to say what's the agent, just flip the word you used. So if it's being reduced, it's the oxidizing agent. If it's being oxidized, it's the reducing agent. Okay, so that's just kind of a summary here. Remember, oxidizing agents are not oxidized. They help something else become oxidized. Okay, to help something else oxidize, lose electrons, they take electrons, which makes them reduced, right? By taking electrons, they end up reducing themselves. Reducing agents are not reduced. They help something else become reduced. And so to help something reduce, in other words, gain electrons, reducing agents lose electrons, which means they end up oxidizing themselves. All right. So in this one, we're just going to figure out what is the reducing agent, what is the oxidizing agent, and what is the spectator ion. Okay, so we'll go through one at a time with the charges. Okay, just like we always will. So what is the charge on this guy? Hey, this is from last topic too, right? We saw this same one. So copper, again, it has two charges, but if chlorine is -1 and there's two of them, this must be copper 2 plus. Okay, chlorine has a charge of 1 minus, always when it's in an ionic compound. Aluminum, all by itself, it's just an atom. All atoms have the same charge, 0, right? Otherwise, they wouldn't be atoms, they'd be ions. Now, things have changed for copper. It's all by itself. It lost chlorine, right? It's all by itself. It's neutral, no charge, 0. And of course, things have also changed for aluminum. Now it's part of an ionic compound, so it's an ion now. Okay, what's the charge for aluminum? It is 3 plus if you look in your periodic table in your data booklet. Okay, chlorine, it's still part of a compound, always has the same charge when it's part of a compound. Okay, so let's take a look here. Let's go one at a time. Copper. Copper went from 2 plus to 0. Is that more negative or less negative? Well, it's going this way. I'm just going to draw the number line so we can picture it every time. I'm not necessarily going to draw in it every time. Okay, but here we have the positives. Here we have the negatives, right? And what's smack dab in the middle? 0. Okay, so to go from 2 plus to 0, right? We are over here. We're at 2 plus and we're going to 0. We're getting more negative. Okay, so that's more negative. And to get more negative, do you have to gain negative electrons or lose them? You have to gain negatives to get more negative, right? So gain negative electrons and grr, right? Leo, grr. Leo the lion says grr. So if you gain electrons, you are being reduced. Okay, so it is being reduced. What kind of agent does that make it? If it's being reduced, what kind of agent is it? Well, by gaining some electrons, it's helping something else lose electrons. So it is actually an oxidizing agent. Okay, let's look at chlorine. We kind of already know this probably, but chlorine is going from, well, it went from -1 to -1. So 1 minus to 1 minus. Okay, if you start at 1 minus, you end up at 1 minus. Did you get more negative, less negative? Well, you didn't do either, right? No change. As soon as there's no change, what does that make this thing? It's there, but is it oxidizing? Is it reducing, right? If the game that everyone's playing, it's there to watch is oxidizing and reducing. It's there, but it's not playing the game, right? It's a spectator to the game. So this is a spectator ion. Okay, last one, aluminum. What's happening to aluminum? Going from 0 to 3 plus. So from 0 to 3 plus. Okay, let's look at our thing. If we go from 0 to 3 plus, hey, that's going away from the negatives, right? That's getting less negative. So less negative. Okay, less negative. Do you gain electrons or lose them? Well, to get less negative, you're going to have to lose electrons, right? Because they're negative. So you must be losing those negative electrons. Okay, if it's losing negative electrons, Leo, losing electrons is oxidation. Now, if it's being oxidized, what kind of agent is it? By losing those electrons, it's helping something else gain them. So that's a reducing agent. Again, this is where I would say get to the whiteboards usually, okay? Try these out. So I would like you please just pause the video, okay? Try this one for sure, okay? Try this one. I think you can do it, okay? See if you can figure out what's the reducing agent, what's the oxidizing agent, and what is the spectator ion, okay? But when you're done, if you want to skip ahead to my answer, you get stuck, you want to see my solution, okay, you can go ahead and press play. All right, I'm going to have to write the numbers underneath this time because I didn't leave myself much room. But this is plain old solid gold, AU, right? Solid gold, AU. So no charge, right? It's an atom, it's a lonely atom. So this is going to have a charge of 0. Okay. So sorry, not sodium, silver, Ag, silver chloride. Now that is an ionic compound. Okay, so silver is part of that. So that means it's going to have its charge. If you look up silver's charge, it's +1. Okay. Now chloride, I guess, has a charge of always the same, right? When it's in a compound, I should say, it can have a charge of 0, but when it's in a compound, it has a charge of -1. All right. Now, things have changed a little bit for gold, right? Gold now has a charge of, if we were to look on the periodic table, it has 2 charges listed, okay? But we know chlorine, when it's in a compound, has a charge of 1 minus, right? So, yes, there's 3 plus and 1 plus listed for gold, but hey, if it only took 1 gold to cancel with 1 negative chlorine, then gold's charge must be not the +3, but the +1. Okay, so that's how we get around there being 2 charges on the periodic table. Now silver is the lonely one. It's all by itself. It has no charge, okay, or its charge is 0, we would say. Okay, so if you didn't pause at the beginning, definitely pause now and see if you can figure out which one's the oxidizing agent, which one's the reducing agent, and which one's the spectator ion. Okay, but I'll go through quick. So gold went from 0 to +1. Okay, again, look at our number line, right? 0 to +1. Is that going away from the negatives? 0 to +1, right? Yes, that's going away. So that's getting less negative. Less negative. And electrons are negative. So if you're getting less negative, do you think you got more electrons or less? You got less, right? You must be losing electrons because they're negative. Okay, Leo, losing electrons is oxidation. Okay, and so if you are oxidizing, what are you? What kind of agent are you? If you're oxidizing, you're losing electrons, right? You're dropping them, so someone else is picking them up. You're helping someone else find electrons. You are helping something else be reduced. So you are the reducing agent because you're not being reduced, but you're helping someone else get reduced. Okay, let's move on to silver. Okay, Ag. So what did Ag do here? Ag went from +1 to 0. So from +1 was its charge, and it ended up with a charge of 0. Okay, now go back to our line. +1 to 0. +1 to 0. Okay, is that going towards the negatives or away? That's definitely going towards, right? Even though it doesn't actually get negative, it's going more negative than it was before. Okay, so that is more negative. And since electrons are negative, if you're getting more negative, right, the only way to get more negative is to gain those negative electrons. Now, Leo Ger, gaining electrons is reduction. Okay? And if you're reduced, if you're taking something else's electrons, well, you're helping that thing lose its electrons. So you're helping something else be oxidized. Okay, so you are the oxidizing agent. Whoops, I said oxidation agent. That's fine too. There's nothing wrong with calling it that either. Okay, lastly, we got, chlorine again, our old friend chlorine. Okay, what's chlorine doing? It's doing the same thing it did before. It's got a charge of -1. It ends up with a charge of -1. -1 to -1. That makes it, whoops, the no change. So that's the spectator ion. Okay, no change. Whoops, forgot to write that. Finally, let's look at this one here. Now, this one contains a bit of a thing that you haven't seen since grade 10. That's okay, don't panic. So when you're looking at this, NO3, okay, that is, it looks scary. This whole big thing looks like, what? Why are there 3 letters instead of the usual 2? Okay, remember, nitrate, NO3, you'll find it in your table of polyatomic ions, okay? So I'm going to give you a sec to look at your periodic table. It's on page 6 half of the periodic table pages, okay? On the top there, a table of polyatomic ions. All you really need to know is that those are a bunch of things that when you stick them together, they end up with a charge and then they behave like anything else with a charge. Okay, so if you find nitrate, NO3 minus, okay, NO3 minus, that behaves the exact same way. We don't have to treat it any differently than Anything else with a charge of -1. So NO3 minus, it might as well say Cl minus or Br minus, any of the ones we've dealt with. All that's important is that it has a charge of -1, okay? Which means in this thing, right, when it's bonded to Ag, it's like any other ionic compound, okay? It's just that this is a little bit more complex of an anion, right? But nothing changes in terms of the bonding or how we treat this at all, okay? So let's just go do it how we always would. Silver, Ag, it's part of an ionic compound, so it's an ion, so it has a charge. What's silver's charge? It's +1, okay? And then like we just said, okay, nitrate, if you find it on your table of polyatomic ions, NO3, notice its charge is NO3 -1, right? -1. If they don't put a number there, it means 1. Okay, nickel all by itself, so lonely, okay? Just an atom, and all atoms have the same charge. What is it? 0, okay? But then over here, again, things have changed for nickel. Now it's bonded to nitrate. Now, if you look on your periodic table, nickel's one of those ones that has 2 charges listed. So how do we figure out what nickel's charge actually is here? Notice, how many nitrates did it take to balance out with nickel? Aha, it took 2 nitrates, right? NO3, 2. It took 2 of them. So if it took 2 -1s to balance with nickel, what must be the charge of that 1 nickel? Must be +2, right? Because it took 2 -1s to cancel it out. All right, so nitrate's charge is still -1, okay? Even though there's 2 of them, each one's charge is -1, okay? So I just want to be clear on that. Even though there's 2 nitrates, each one still has a charge of -1, okay? And that's what we're writing when we write these, is the charge of each thing there. All right, and then poor lonely silver now. Silver is the one that ends up alone in the end, okay? It has no charge. It's just an atom. Just realized I got kind of weird on my color coding there. That should be purple if I'm keeping things consistent. Okay, right away, can you pick out the spectator ion? What would the spectator ion look like? How would its charge change? Aha, trick question. Its charge wouldn't change, right? It would stay the same. So what thing here had its charge not change? And it sticks out like a sore thumb now when you look at it that way, right? Well, nitrate. So NO3 minus went from -1 to -1, which is no change, which means it didn't gain electrons, it didn't lose electrons, which means it didn't oxidize, it didn't reduce, but it was there, it was spectating. Okay, cool. Silver, what did it do? Went from +1 to 0. Silver went from +1 to 0. Okay, on our number line, right, which way is that going? Picture the number line in your head, it's getting more negative. It's going towards the negative side, right? So more negative. Okay, to get more negative, what do you have to do? Gain those negative electrons or lose those negative electrons, right? To get more negative, you got to gain negative electrons. And Leo, Gur, gaining electrons is reduction. Gur, Gur, Gur. That's reduction. This question didn't ask us if it got reduced. It asked what's the oxidizing and reducing agents. So if it got reduced, what's it helping something else do? Get oxidized, right? So that makes it the oxidizing agent. There we go. Okay, finally, nickel. So by process of elimination, you can probably figure out what nickel is going to be here, okay? But let's just go through it for the sake of practice. Nickel went from 0, and it ended up with a charge of +2, okay? Now picture your number line. Is that going away from the negatives or towards them? All right, that's going away from it. So that is less negative. All right, now you're going to get less negative. What do you have to do? Gain negative electrons or lose those negative electrons, right? If you want to get less negative in your life, do you have to get rid of negative stuff or add more negative stuff? You got to get rid of it. To get less negative, you got to lose electrons, okay? To lose electrons, Leo, losing electrons, Li is O, oxidation, okay? And so if you are getting oxidized, if you're losing stuff, you're helping someone else gain stuff, right? If you're dropping money on the street, someone's picking it up, you're helping someone else gain money. So you are the reducing agent. You're not reduced, but you're helping someone else get reduced. Or maybe not you, but nickel anyway. Okay, so that wraps up this video lessons topic. Okay, you can now do some more of the formative work for this as we keep working through this week.